So now that we've talked about decision making, we can start to talk about what framework we have for thinking about the effectiveness and the inherent risk that we take in making those decisions. To do that, we could create something called a decision-making matrix. So in a decision-making matrix, we are organizing two different kinds of... so in other words, we are balancing the true state of nature and our decisions. So the true state of nature, we're talking about the null hypothesis. And for the null hypothesis, we know that it's either true or it's false. And again, we may never know which one it is. So that splits us into two different realities in which we make our decisions. So we might reject the null hypothesis, or we might fail to reject the null hypothesis. There are two cases here where we've made the correct decision. So if we fail to reject the null hypothesis when in fact it's true, that's a correct decision. If we also reject the null hypothesis when it's false, that's also a correct decision. But what happens when our decisions don't line up with reality? For instance, we might reject the null hypothesis when in fact it's true, which would be correspondingly a false negative. And a false negative is a type 2 error. So we're rejecting the null hypothesis when in fact it's true. And that is a mistake that we're going to balance against the other kind of mistake, which is if we fail to reject the null hypothesis when it's false, is a false positive, which we call here a type 1 error. So for the sake of illustrating these different decisions, let's think about quality control, and we're in the business of the production of a certain kind of machine. Maybe it's a U phone. And we rely on some key measurement that indicates that our process is under control. So it could be something like the mean number of defective units in a test batch. And as long as that mean is lower than some threshold, then everything is fine. But if that mean happens to be greater than that, then our production process has some serious issue. And in your line of work, you're responsible for sounding that alarm. These work stoppage may be expensive, but hopefully it's necessary. So we're thinking about some hypothesis test that may look something like, we assume the null hypothesis is that our mean is equal to 10 and that the mean could be greater than 10 in the alternative hypothesis. So in this trade-off between our two decisions and our two possible realities, the null hypothesis indicates if this is true, then everything is okay. And if the alternative hypothesis is true, or in other words, if the null hypothesis is false, then there's a serious issue. And let's just say, so suppose we take some sample mean, and we find that it's 11.3. Close enough to 10 that it may or may not be significant, but it is greater than 10, so to some extent we are justified in sounding the alarm here. So again, there's 4 different possible scenarios here, depending on which one is true and what we decide to do. So in the first case, let's suppose that H0 is true, so the mean is equal to 10, and we fail to reject the null hypothesis. So you're not saying there's sufficient evidence to say that it's not equal to 10. The sample mean is close enough that it's fine. So in this case, the production process is actually fine, and you've decided to proceed as usual. It's a correct decision. No one needs to comment further. Basically, business as usual. In the second case, let's suppose H0 is true, but you reject H0. So in the context of the scenario, what we're saying is the mean is actually equal to 10 or less than 10, but based on your sample mean, you've decided, no, we should reject that reality. It is in fact true that mu is greater than 10, or so we think. So in this case, the production process is fine, but we've sounded the alarm. The process is halted, and it's a costly stoppage, but with no issue identified. Ultimately, you're only reprimanded for being overly cautious, but at least nothing went wrong. So this is a type 1 error, a false positive alarm. And, maybe this is a costly error, but ultimately it's fine. In the third case, let's suppose H0 is not true, so it's false. The mean is actually greater than 10, but you failed to reject H0. In this case, there is some serious issue where the number of defective units is high enough and you have decided to say everything is fine, we don't need to comment any further. In this case, we've made a type 2 error, a false negative, and this triggers an expensive recall and you are fired. The fourth case is if H0 is false, so there is some error, so the mean is greater than 10, and you reject the null hypothesis. So you have sounded the alarm, there's an issue, and you end up commended for your correct decision. Promotion? Question mark. All right, so in this case, right, there are 2 errors that you could make, the type 1 and the type 2 errors. A false positive or a false negative. Both are things we want to avoid, but sometimes we can't avoid them. In this event, and more generally to any kind of hypothesis test, we are looking at a trade-off between a type 1 error and a type 2 error, and we're going to think about which one is least desirable. So, from your perspective as a U-phone production quality control manager, you are going to look at a type 1 or a type 2 error and the possible outcomes and decide which one is preferable for you. Perhaps for you, this one is less objectionable than this one. In other words, you would rather make a costly mistake that is overly cautious than to get fired for not being cautious. And this level of risk that we're trading off, we call the level of significance. Namely, the probability of making a type 1 error. So the probability of making a type 1 error is the probability of rejecting a true statement based on sample data that simply occurred by chance, is the level of significance that we denote alpha. On the other hand, the probability of making a type 2 error is 1 minus beta. So we have here two constants. The level of significance is alpha. 1 minus beta is called the power of the test. So the probability of making a type 2 error in this case, or in any case, is when you have a null hypothesis that is not true, but you fail to reject the null hypothesis. And every hypothesis test is a trade-off between significance and power. We want a low level of significance and we want high power, but having one affects the other, and we can't, in every case, have an optimal decision.